So the natural choice of axes would look like this. You can draw a y-axis in this direction, and you could point an x-axis along this direction, so that the unit vector in this direction would be I hat horizontally, and the vertical unit vector would look like j hat, right? Okay, now we can write all of those vectors, we can translate all of them into, we can resolve all of them in this coordinate system. That would, so let's correct those one by one. You can have this one would be, for let's say start with book 2, the force of gravity would be written like minus m2g j hat. The normal reaction force N12 would be N12 j hat, right? Let's remove those. That's right. And the force of static friction, which is acting to the right, would be given by mu s N12 I hat. Okay, in body 1 we would have, okay, this force of static friction would be given by minus, because it's pointing to the left, right? So we would have F static friction equal to minus mu s n1 comma 2 I hat. The force of normal reaction from book 2 on book 1 would be given by minus n21 j hat. The force of gravity is minus m1 g j hat on book 1. The force of kinetic friction is equal to, since it acts to the left, it's minus mu k n g1 I hat. The F max is F max times I hat. The force of normal reaction from the ground on body 1 is n g1 j hat. Okay, so we've managed to translate or resolve all of these vectors in our choice of coordinates. Now we have to apply Newton's second law on both body 1 and body 2. Remember that both of these are moving with some common acceleration a, and actually in this coordinate system that acceleration can be written like a times I hat, right? Since we have all the forces resolved in these components, it's easy to find the net force. Let's start with body 1. So Newton's second law states that the net force on body 1 would be equal to m1 times a. In this coordinate system, of course, we've written the acceleration as a I hat, and it's the common acceleration. Both body 1 and body 2 have this acceleration. So we want to write down net force on body 1 as a vector. All we have to do is we have to add these 6 arrows. Once we've selected coordinate system, it's very straightforward. So let's add component by component. For I hat, we have minus mu s in 1 comma 2 from the static friction. We have plus F max. Then we have minus mu k in g comma 1. That's it. That's the 3 horizontal components of the net force. Then we have, with j hat, we have n g comma 1. We have minus m1g from the weight, and we also have minus n2 comma 1. And we have this equal to m1 ai hat. So now that we have a vector equation that's equivalent to 2 scalar equations, right? So if we want to write those down, that is, you want to compare the components of I hat and j hat, the coefficients. If you compare that, then you get the following two equations. You have minus mu s n1 comma 2 plus f max minus mu k n g comma 1 equal to m1a. Call this equation 1. The other equation goes n g comma 1 minus m1g minus n2 comma 1 equal to 0. No j hat component on the right hand side. So let's do this for body 2 now. So once again, for book 2 you have the net force on book 2 equal to m2 times a I hat, right? Because they're moving with, of course, once again, common acceleration, a I hat. So you have mu s n1 comma 2 I hat plus you have n1 comma 2 minus m2g times j hat equal to m2 a I hat. If you compare the I and j components in this equation, you can come across these two scalar equations. You have mu s n1 comma 2 equal to m2a. Call this equation 3. And n1 comma 2 minus m2g equal to 0. Call that equation 4. So altogether, now we have these 4 equations. What we want to do is we want to solve them to find this f max. The known quantities in these equations are mu s, we know mu s, we know mu k, we know m1, and we also know m2. What we don't know are, of course, we don't know f max. We also don't actually know the normal reaction forces, right? We don't know these, and we don't actually know what the common acceleration is either. If we can solve for the normal reaction forces and acceleration and plug those into equation 1, we should get our desired f max. Okay, so how do we do that? First of all, we know something. We know that n21 and n12 are third law pairs. We can say that n21 equal to n12 equal to, let's say, nb, right? Because they're third law pairs, their magnitudes are the same. So let's replace n21 and n12 everywhere in these 4 equations. So plugging that in, we get these 4 equations. Let's be clear about what we just did here. As you remember, these normal reaction forces are third law pairs, right? What that means is that these two vectors point in opposite directions, but their magnitudes, which are n12 and n21, are exactly equal. That's all we have plugged in into these equations. So the next thing we can do is we can solve for nb. Let's take the 4th equation, right? Let's take the 4th equation. From 4 we have nb equal to m2g. That's something we can ultimately plug into equation 1. Okay, again, from equation 3 we can find an expression for a, right? Because from 3 we have, from 3, a equal to mu s by m2 and b. But we've also found the expression for nb in terms of mass, and then what we get is plug this nb equal to m2g here, you get A equal to mu s times g. Does that make sense dimensionally? Yes, it does, because mu s is a dimensionless constant and g has dimensions of acceleration. We can plug in nb into equation 2 as well and get a value for ng comma 1. So from 2 we get ng comma 1 equal to m1 g plus nb, but nb is m2g, so m2g equal to m1 plus m2g. Does that make sense, by the way? ng1 is the normal reaction force from the ground on 1, which, I mean, that should be equal to the weight of this whole system, because you are not providing any other vertical force on the table, and the weight of the whole system is m1 plus m2g. So that makes a lot of sense, right? At this point you can plug in all three of these equations into equation 1, right? Plug those all in and you can get a expression for F max, that is in terms of m1, m2, mu s and mu k, which are all known values, and you can use those to find a value of F max. We invite you to do that simplification and use the formula to solve the next quiz. Thank you.